This slideshow gives a brief explanation of the graphical interpretation of the eigenvalues and eigenvectors of a covariance matrix. From the following graphs, we can see that the overall distribution of the data determines the covariance matrix. For example, in the first graph where the two variables are positively related, in other words, as the one increases, the other variable also increases, we see that the covariance between the two variables is positive, that is 4. In the second graph, where the relationship is negative, the covariance is also negative. This will give a negative correlation coefficient between the two variables. In the last two graphs, where we do not see a linear relationship, the covariances are 0. In the first case, the variance is largest in the x direction. That is, the variance of x is equal to 5 as opposed to the variance of y, which is equal to 1. In the second case, the variance is largest in the y direction, and this is also reflected in the covariance matrix. As an example, we study the measurements that were made on the flower Iris virginica. The flower has a petal and a sepal, and 4 measurements were made on each of 50 flowers: the petal width, petal length, and the sepal width and length. A part of the data set is given in this table. The 4 measurements for each flower is given in a row, say petal width, petal length, and sepal width and length for the first flower. Measurements for different variables are given in different columns. The first column has the measurements for petal width for the 50 flowers. Because we have 4 measurements on each of 50 flowers, the dimension of the data matrix is 50 by 4. The next slide shows scatter plots for each variable against the other variables. For example, this is the plot of sepal length against petal length, and we can see that there is a positive linear relation between these two variables. When studying these two variables, we calculate the sample mean and sample covariance matrix. The sample mean gives the central location of the data. The mean petal length for the 50 flowers is 55.52, and the mean sepal length is 65.88. The data is centered around this coordinate. The positive value of 30.33 for the covariance between the two variables means that there is a positive relation between the two variables. We also see that the variation in the measurements for petal length is smaller than that for sepal length. Using this to calculate the correlation gives a value of 0.86. Next, we look at the eigenvalues and normalized eigenvectors of the covariance matrix. Starting with the eigenvector that corresponds to the largest eigenvalue, we draw this vector from the center of the data. This vector will point in the direction of the largest variance of the data. The length of this vector is proportional to the corresponding eigenvalue of 66.18. In a similar way, the eigenvector of the second largest eigenvalue can be drawn from the center point of the data to determine the direction of the second largest spread of the data. This vector will always be orthogonal to the largest eigenvector, and its length is proportional to the corresponding eigenvalue of 4.71. If we assume that the two variables have a bivariate normal distribution, we can use the vectors as axes to draw an ellipse around the data. Measurements observed for Iris virginica will fall within the ellipse with a certain probability. If the measurements for petal length and sepal length on the flowers of an iris fall outside the ellipse, we will be able to calculate the probability that the flower is not an Iris virginica. Eigenvalues and eigenvectors of covariance matrices play an important role in understanding and analyzing multivariate data.